In today's lecture, we're going to discuss the tailoring of composite plates for dynamics and buckling characteristics. Very specifically, in today's lecture, we're going to discuss the waypoints on how to do that, but the goal in this particular lecture is not to go through a comprehensive theory of dynamics and buckling, but mostly to really discuss the fact that you can tailor composites. That's really the bottom line of this particular lecture, is to demonstrate that tailoring of composite structures is possible for these two applications. So we had previously discussed the simply supported plate subjected to a distributed load. And we assumed that the plate is symmetric, which I think is a good design choice because a symmetric ply layup does not involve the B matrix, which is the extensional bending stiffness coupling term, as you recall, which connects the stress resultants that are acting in the in-plane direction and connects them to the moment resultants. So to decouple the two, choosing the bending stiffness, this B matrix to be zero entails making the composite symmetric in ply stacking sequence. And so as a consequence, we can neglect all these terms. And if we assume then the bending twist terms are close to zero, then we can now simplify the equations for a simply supported plate subject to a uniform load. We had previously solved this problem for using the Navier's solution. And so what if we replace this load here with a dynamic term? And we're going to replace it. You can see here that this is very similar to a mass times acceleration, and that this term here represents the deflection through the thickness, but the time derivative of that twice, which really represents the acceleration in that direction. In addition to that, h represents the thickness and rho is the density. And so by doing so, we have simplified, or we have basically stated the dynamic problem for a composite structure. So if we assume a periodic solution that looks like this, we have W naught, which represents the transverse deflections of the plate, and note that it could be time varying. We make that equal, and by using separation variables, we have this coefficient Wmn, sine alpha x, sine beta y, ei to the omega t, and what we want to really do, and note how alpha is n pi a and beta is n pi b. So this, as we stated earlier in the previous lecture, we demonstrated how by selecting these sign functions, we can automatically satisfy the boundary conditions for simply supported plate, which means that around the edge of the plate, you should not have any deflections. And we can see here that if I set m equals x equals a cancels out, you get m pi, and sine is a multiplier to pi where m are integers. So therefore, sine will be zero, and this goes to zero. The same turns out for this term. So you can see how around the edge, it does satisfy the boundary conditions if the plate were A by B, okay? We also notice that at the edge boundaries, the moments are also zero, and that entails a second derivative of W. And again, second derivative of sine function gives you a sine function again. And so you can see how automatically this also supports that type of boundary condition. So this satisfies those boundary conditions exactly. We also want to point out here that what we really assumed here, as the previous lecture, is a summation series, which could be infinite series from m1 to infinity, and summation from n1 to infinity. I didn't write the summation symbols because m and n are repeated. Notice how alpha has an m and beta has an n. So m and n is repeated. So what we're talking about here is a double summation series of m and n. I also want to point out how we've separated the variables. So here's a spatial domain, these terms right here, while EI omega t represents the time domain. So by doing so now, I can substitute this expression into the partial differential equation. And when I do that, you will notice how EI omega t, if I take 4 derivatives of this, sorry, not 4 derivatives of this, but if I take 4 derivatives of this whole expression with respect to x, EI omega t acts like a constant. And so you really only have derivatives of this with respect to x, but notice how the sign, these two sign functions, we've also separated variables there. So this only accounts for x, this only accounts for y. And w is really a constant. So therefore, this derivative is fairly simple to do. Feel free to pause the video to see if you can find, substitute this expression into this and see if you can get it right. I will give you extra credit if you're able to go through that. So pause the video. If you don't want to pause the video, continue listening. But if you were able to get it, congratulations for being the king of complex variables. So the derivative of this deflection here with respect to x really is only this derivative sine function, but 4 times, which will give you alpha to the 4th with this coefficient here. And then you can do this derivative and then get beta to the 4th with that derivative there. And then here you have a derivative with respect to x squared and y squared. So you actually get alpha squared and beta squared, but with this term again showing up as a coefficient. And then for this last term, what we have is a derivative of w with respect to time derivative twice. So that means I have to take the derivative of this twice, and the derivative of e to a function, to an exponent, is really e again. And so that's why this shows up against as a coefficient, but now we only have this omega showing up, omega squared. And then we have this rho h that's left over. So then we have this equation times this coefficient, and we notice how what's inside the bracket must be true and must be equal to 0. So that's one potential solution. Another potential solution is that w is 0, but that just corresponds to a plate that's flat and is doing nothing. But what we're most interested is in trying to understand what is going on with this plate in terms of the vibration, the natural vibrations of this plate. And so if I solve for omega in this equation, which it is a trivial solution to the problem, what I found here is that we've able to solve for omega. Pi is 3.14159. A is one edge of the plate length. Rho is the density, H is the thickness. And so D11, D22, D12, D66 are the components of the bending stiffness D. M and N are basically quantities that have to do with the summation series that we had here, okay? And so this one here, if I put M of 1, so sine with an M of 1, that's really a half sine wave. So note how the lowest, if I want to look at the, the fundamental frequencies, normally you want to find the fundamental frequencies and find the values, the lowest fundamental frequency, and then in order find them all. And so you can see clearly here, since omega is directly related to m to the 4th, n to the 4th, and so forth, then m and n equals to 1 gives you the lowest fundamental frequency. And then you have other natural frequencies with varying values of m and n. So for vibration, it is an important aspect of engineering design. Why? So if you have a structure that has a natural vibration frequency, and you have a structure that's subject to a loading environment that has a frequency content that could couple with the natural frequencies of the structure, then there's a potential there that you could have resonant condition. And so typically in design, we want to keep the natural frequency of the system and the driving forces of the system, the frequencies of the driving forces of the system. We want to maintain a separation so they don't couple and cause a plate to fail. You know, that is one of the things you can use, you can tailor composites for, is to be able to drive that. You can drive the design to do so. The second thing I want to discuss a little bit more is that natural frequency also is known as eigenfrequency. And this is the frequency at which a system tends to oscillate in the absence of any driving or damping force. This motion pattern that you may see of a system oscillating at its natural frequency is also called normal mode. I invite you to look at my other YouTube videos where I may have a discussion on dynamic analysis. And so in continuing this conversation, is that we could now apply some of the optimization concepts that we talked about before in the previous lecture. And what we can do is, let's study an example so you can see how, so again, the purpose of this particular lecture is to demonstrate to you that it is possible to tailor composites for a particular goal, design goal. So consider a composite material with the following lamina properties. And let's assume that each ply is 0.005 inch with the following properties for the lamina. The plate is 20 inch by 15 inch and it has 16 layers. Then density is this much. And what we want to do is find an angle ply symmetric laminate such as the frequency of the plate is maximized. So what we want to do is maximize the frequency of this plate. That is the goal of this problem. And so let's look at what we've done here. We've set up the problem to provide the material properties on the top here. We've also are tracking these parameters here, D16, D11, D26, and D11. So notice how we're tracking that, because we already made an assumption here where we want these terms to be small, D16 and D26. If they're not small, we have to be careful because we made some assumptions with that. So given that information, we can now calculate Q11, Q22, Q12, and Q66. That's a Q matrix that depends on these material parameters. Now here are the plate dimensions A and B. We can, change them, but for this particular problem, A and B were given as this. We also have the calculation of the D matrix. So that's another important consideration. And what we want to do is find the ply angles that will, again, maximize that density. Again, here we fixed the number of plies. So here we're talking about 8 plies. And so that's why you see here 8 plies. And this calculation here is the Z cubed minus Z cubed term, top and bottom. So Z top cubed minus Z bottom cubed. This term right here is the one that's used in the D matrix calculation. And notice how I'm going to track the D16 to make sure, and D26 to make sure they're small enough compared to D11. And then the next step is to then calculate omega n. And what I want to do is to make sure that I maximize the frequency by finding this ply angle. That's a goal. Maximize the frequency as much as I can to be able to maximize this fundamental frequency. We know that the lowest frequency you could get is at n equals 1 and n equals 1. So we'll track at least that. And if that's high, we've maximized it, and the other frequencies also will be higher. But we're going to focus on the fundamental frequency. The lower frequencies typically contain the most energy for low frequency loading applications. So that's one reason why we could be focusing on that. So let's study that problem now. So let's go to Excel and see how we've done this. Again, this column is used so that we can then calculate the D matrix. So this is where this is coming from. And the summation of this is used directly into the omega calculation of frequency. You can see here pi squared, and all this formula has been plugged in here. And that's for the first frequency. We've done that for the first frequency. And again, our goal is to maximize, basically find out the Planck angle and maximize the frequency. So, one option is to start with 0 degrees, and we could then go from there. We go to data and then solver, and then what we want to do is maximize this particular value. And so we can hit solve, and then when we do that, we find the actual answer is 55 degrees for the Planck angle, plus minus 55 degrees. And you can see here that the frequency did increase to 67, and that is the maximum value. You could play around so you can see that is the actual solution to the problem. Now, you could make this problem a little bit more advanced. We could also look at the situation where we want to look at the other frequencies higher than the fundamental frequency. So we can get that with 1 and 2, 2 and 1, and 2 and 2. Here are your frequencies. And then we can start with 0 degrees and see what happens. Again, that's low. And so let's see if the solver finds a solution for that. We're going to change the Planck angle and see where that goes. And you can see here that I still get 55.37 as a solution. So it actually pushes all the frequencies up for this particular issue. So we have found that the angle pi symmetric laminate of plus minus 55.37, 4 of them symmetric, was found to be a solution that maximizes the frequency. And I also checked really quick and ensured that these parameters are less than 0.2, which is required for the solution that we were pursuing. So that is good. Let's look at the optimization problem 2. In problem 2, the idea is, hey, consider the composite material with this lamina properties, with this plate dimensions, and it has 16 layers. We want to design a symmetric laminate such that the fundamental frequency is 60 hertz and the second frequency is on 120 hertz. So there's too many possibilities for laminate. So what if we selected something like this or like that? And so we're going to use the algorithm to determine the angles for the design that can lead to this targeted. We're targeting particular frequencies. In the previous problem, optimization problem number 1, we were maximizing the frequency. In this particular problem, we're trying to target a particular frequency. And we want the first one and the second one to be a particular value. So the question is, what will that be to get us there? And so we can do this one. Let's select that one as a possibility and see where that takes us. And I'll show you that it's going to be pretty much the same spreadsheet, but now what we're going to do, we're going to try to target the first and the second frequency, and we're going to let the Planck angles be whatever they need to be. What we want to do is to make sure that if this is the frequency I'm calculating through this formula for particular Planck angle, what I want to do is to minimize this error. So I want to take this frequency and the targeted frequency of 60, and I want to take that difference and square that. And I also want to take the targeted frequency of 100 minus the second fundamental frequency, natural frequency, and I want to square that. And what I really want to do is minimize the error. If I can minimize the error, then I'm forcing this 65 to become more like 60, this 134 to become more than 100, more like 120. That will first force the GRG optimization method to find the best Planck angles that will make that happen. So let's see how we approach that. So again, this is how we set it up. Here's the lamina properties. Here's the Q matrix, and this is the invariants that are used to calculate Q1 bar, the Q bar matrix, right? And then which are used to calculate D11, the D matrix, the bending stiffness matrix. We also have the ply angles, and we talked about wanting to target a very specific ply angle sequence. We had a stacking sequence, and we only want to vary 2 ply angles to make this happen. Here's a frequencies calculator with everything at 45, and this is what you get, and I want to target 60 and target 120. And so this is the error that I want to minimize. So we go to the solver, and what I want to minimize G27, the cell G27, which is this one right here. If I can minimize the error between the target frequency and what I got, then I should be somewhere where I need to be. And I want to change C18 and C16, which drive, C18 and C16 drive the ply angle here. These 2 values drive the rest of it. So let's hit the solve command, and what we get is that, yes, I was able to get the frequencies at 60 and 120 for the first 2, and the ply angles I need, these are ply stacking sequence that can make that happen. So this is how you will deal with this particular problem. And so here is a solution to the ply stacking sequence that Excel has come up with. This is your ply stacking sequence and minimizes that error. And so we're able to get to a reasonable solution here. So now I want to see if I can get the ply stacking sequence that looks like this one. That is the next goal now. So let's look at that one. So here we are. We set up the problem the same way. And we want to minimize the error in the same manner. So I'll hit the solver command, hit solve, and we're able to find a ply stacking sequence that will minimize the error. The error, you know, it's not perfect. This is 4 hertz off, but it's not too bad. And it gets us close enough to what we need. So the ply stacking sequence then becomes plus minus 60.33, 2 of them plus minus 0 degrees, 2 of them symmetric. Okay, so let's look at the third problem here, optimization problem. What we want to do is find the minimum thickness and ply angle. So the first fundamental frequency is at least 50 hertz. And so that's the one we're going to study. And we're going to use the idea of, and note here that we want to find the minimum thickness now. So this is a little different. In previous problems, we kept the number of ply angles, the number of plies fixed. Here, we want to find the minimum thickness that will make this happen. And so for that, we again have to use the idea of design choice, where we use this binary variable V that either activates the ply angle, the ply, or not. And what this does, it forces you to ensure that there's no middle plies in between that could have a 0. So we don't have empty plies in between. We don't want to have that situation. So we enforce that with this constraint, and what we want to do is at least have the frequency to be at least 50 hertz. And that's the question that is being asked. We again use the constraint to ensure that this formula always is true. So Vk minus 1, that always has to be, Vk minus 1 minus Vk always has to be greater than 0. And so we put that constraint to be the case, and we'll you know, find what needs to happen for this to occur. So we can get the solution that will basically give us at least 50 hertz. So that is a goal that we want. And so let's go and study that problem in particular. And because there are a lot of different types of solutions, we're going to select the 090 plus minus A, and we're going to find A, and then we're going to set everything here 1, and let the solver find the minimum thickness in that manner. So we'll just let it run the analysis and then figure out what is the ply angle here and how many of them I need to get the frequency of interest. Okay, so this is what the solver found. It just found that I don't need any of these plies, and I just need 8 plies or 7 plies symmetric, and with a ply angle 55 will get me to minimize the frequency down to 55. Note that if you increase the number of plies, you increase the thickness. And if you look at the solution for the frequency, increasing the thickness will have an effect um, on the frequency content of the part. So it is directly related, and you can see here how that was addressed. Okay, so looking at buckling, structures also have to be designed for buckling failure mode, and buckling really occurs when you apply compression and shear, and the structure loses stability. And so losing structural stiffness due to the applied loading is considered buckling. You will see through a YouTube video that I go through buckling. Check it out. But for now, my goal is to explain what the equation looks like for a biaxially loaded plate um, that for which we're applying compressive load. And the compressive load will basically will add these two terms. Um, N naught is the magnitude of the load applied in one direction, and K times N naught is the magnitude applied in the other direction, in the Y versus the X. And so what we want to do now is solve this equation, figure out what the buckling load is, and again, we'll substitute a spatial trial function that looks like this. It's an infinite series. In this case, there's no EI omega t because we're not solving a dynamic problem. We'll substitute this into this equation, and then this will become a coefficient. Now we can solve for N naught, and when we solve for N naught, now we get that the critical buckling load is the lowest value of N naught for all combinations of M and N. Notice here how M and N shows up here also in the denominator, and M and N is also in the numerator. So you have to be smart about how you figure out what the critical buckling load is for all combinations of M and N. So optimizing for buckling is a little bit harder because the idea now for buckling is really to maximize the critical load. We want to increase this maximum load as much as you can. And so you have to then, for each laminate design, select the highest value you can for N naught for all combinations of M and N. So this is incorrect. We want to find the maximum value of N naught, not the minimum value, that will be able to give you the maximum value. And you have to basically vary M and N, but also you have to come up with the stacking sequence. That can be done using the methodologies that we have discussed today, but we will not be able to do it today. My point is that it is possible to basically optimize the buckling load by tailoring composites. So my goal for today was not to give you an extensive um, education in the area of dynamics and the area of buckling. My goal today was to demonstrate to you the composite angles and the thicknesses can be tailored to give you optimal buckling behavior, and then they can tailor composites so their dynamic characteristics can also be tailored in that manner. So with that said, I hope you enjoyed today's lecture, and it's a fairly short lecture, but it should be enough time for you to uh, kind of continue understanding classical play theory and then the optimization video that we had the previous week. So I hope that you're building on and taking this time, which is a shorter video, to kind of play around with Excel sheet, understand what is going on with the optimization algorithms. So have a good day and stay safe, and see you later.